Hi, I'm Rebecca. In this lesson, we'll learn about the graphs of some basic functions and properties associated with graphs. Let's look at our specific objectives now. We'll consider continuity, the identity, squaring, and cubing functions, the square root and cube root functions, the absolute value function, and piecewise defined functions. Let's begin with an informal definition of the term continuity. A function is continuous over an interval of its domain if its hand-drawn graph over that interval can be sketched without lifting the pencil from the paper. Now we're going to look at a couple of examples where we're going to see how to use this definition. Determine the intervals of the domain over which each function is continuous. Here's our first example. Now, what we'll do is basically just start tracing the graph, and as long as we don't have to lift our pencil in order to trace the entire graph, then we can say that the graph is continuous over its domain. Now, this graph is continuing over to the left and downward, and over to the right and upward. And so we can say that this graph is continuous over its entire domain from negative infinity to infinity. As a second example, let's consider this graph where we have a portion of a line drawn out and another portion of a line. As we start tracing the graph, we move from left to right. We're going to notice that we trace down, but in order to get to the other portion of the graph, we have to lift our pencil in order to continue. For that reason, we're going to say that we have a discontinuity at the value of x equal to 1, and so we would write down that this graph is continuous from negative infinity to 1 and from 1 to infinity. Now we're going to look at the graphs of some basic algebraic functions. Here's our first one. It's called the identity function. It has the formula f of x equals x. Now, this function really pairs every real number with itself. What we can do is start by drawing out an xy chart, and on that chart we're going to substitute some values for x. We'll just take a basic setup, negative 2, negative 1, 0, 1, and 2, and we'll now replace the x in our formula with these values. So if x is equal to negative 2, our functional value is also negative 2. If x is equal to negative 1, we come up with negative 1. If x is 0, our y is 0. If x is 1, our y is 1. And if x is 2, our y is 2. Let's plot these 5 points. Negative 2, negative 2. Negative 1, negative 1, the origin, 1, 1, and 2, 2. We're now going to connect these dots and form a straight line, which you'll notice gives a diagonal going through the first and the third quadrants. We also want to look at this graph and identify the domain, and we'll abbreviate that with a D. The domain is going to be from left to right, negative infinity to infinity. Our range, we can look at the graph from bottom to top. That goes from negative infinity to infinity. We can also identify the fact that this is increasing over its entire domain. So we can say that we have an increasing portion from negative infinity to infinity. And then finally, we can note that we could draw the entire graph without lifting our pencil, and therefore it is continuous over its entire domain, and that is from negative infinity to infinity. Let's also look at how we graph this on a calculator screen. We're going to take a graphing calculator and we're going to go to where we input the value for the function. Here I'm going to press y equals. I'm going to put in my variable x, and then I'm going to press graph. And we note that we're going to end up with that same picture, the diagonal which goes through the first and the third quadrants. Now we're going to move on to another basic function. This is called the squaring function. It's going to pair with every number, that number's square. Let's do the same process. We're going to start off by drawing an XY chart. We'll substitute in values for x, and I'll just pick some basic ones, and come up with values for y. Remember that we're going to square every value of x. So negative 2 squared gives us 4. Negative 1 squared is 1. 0 squared is 0, 1 squared is 1, 2 squared is 4. Let's plot those points. -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. We'll now connect the dots, forming a shape that looks like a U. It is called a parabola. And now let's identify the domain, range, and where it's increasing and decreasing, and then also where it's continuous. For the domain, we look at the graph from left to right. The graph continues on toward the left infinitely and continues on toward the right in the same manner. So our domain is going to be from -infinity to infinity. For our range, we look at our graph from the bottom to the top. The first time we end up with a y value is here at the origin. That y value is 0. And we notice that we're also getting all y values greater than 0. So we're going to have our range from 0 to infinity. Notice that this graph, as we move from left to right, we have a portion of the graph that decreases, then we get to the origin, and then we have a portion of the graph that increases. We can say that the graph is decreasing from left to right, -infinity, until we get to 0, and we'll include the 0. And we have it's increasing from this point at the origin toward the right. That's from 0 to infinity. And then we can also note that the graph is continuous. As we move from left to right, we can draw the entire graph without lifting our pencil, and therefore it's continuous on its entire domain. That is from -infinity to infinity. Let's next look at the same graph on a calculator screen. And so we go to our y equals, and we're going to replace y1 with x squared. We'll now press graph and see that same parabolic shape on our graphing calculator. Let's continue raising the power on x. Our next example is a cubing function. The formula is f of x equals x cubed. We'll do the same process. Let's substitute our basic values. We're going to cube each of these values. -2 cubed is -8. -1 cubed is -1. 0 cubed is 0. 1 cubed is 1. And 2 cubed is 8. Let's plot these points. -2, -8. -1, -1. 0, 0. 1, 1. And then 2, 8. Now this graph is going to have a curve to it, but it's going to be very steep. Notice that in the first quadrant, it kind of resembles that same shape as the x squared graph, but it obviously is not going to the same values. Let's think about each of those properties of the graph that we're interested in. The domain. This graph continues on to the left and continues to the right. We could substitute in any value we'd like to for x. So our domain is going to be from -infinity to infinity. As we can see on the graph, we have all values down to -infinity and all values up to +infinity. So our range is also all real numbers, -infinity to infinity. As we move from left to right on this graph, we'll notice that we continually increase. So we can say that our graph is increasing on its entire domain, which is from -infinity to infinity. And we did not have to pick up our pencil as we were moving along, so it is continuous on its entire domain from -infinity to infinity. Once more, let's look at a calculator and see how that looks on the graph. We're going to have y equals, and we're going to have x, and there's two ways to put in a cubing function on this calculator. One way is to press the math key, and then notice that the third entry is going to be a cube. That way it looks like an exponent, x cubed. Another way to do it would be to use this power key where you have a little caret and then you put in the cube. Either way will give you the following graph. And that's the same graph that we saw when we were doing it ourselves by hand. Now that we've looked at raising to different powers, we'd next like to consider taking roots. Let's see what those graphs look like. We'll begin with the square root function. F of x equals the square root of x. Now this time when I'm picking my values for x in my chart, I'm going to notice that if I try to substitute in any negative value, I will not get a real number back. The square root of a negative number is undefined in the set of real numbers. In fact, the smallest value that I can substitute in for x is 0. We also note that we can now choose numbers that are going to be nice as far as trying to plot them. So I can take the square root of 0 and get back 0. If I take the square root of 1, I get back 1. Now I could write in here a 2 and get back square root of 2 and then approximate it. Or I can just choose another number whose square root is going to be a whole number. And that is, if I go ahead and go to the square root of 4, I can come up with my value of 2. If we go to square root of 9, we come up with a 3. Let's just start by plotting these points. We're going to have the origin 0, 0, the point 1, 1, the point 4, 2, and you can see that as we would move out on this graph, the point 9, 3, it's going to be a gradual increase. We'll connect the dots in order to get this shape. Let's next identify those properties of the graph that we're interested in. Our domain. Well, as we mentioned previously, we cannot substitute in any numbers smaller than 0. So our domain is going to be from 0 to infinity. What about our range? Well, as we look at the graph, notice that we're also not getting any y values that are negative, but we are getting back a y value at 0, and we can get back any other y values greater than 0. So our range will be from 0 to infinity. As we move along the graph from left to right, we notice that our pin is continually increasing. So this graph increases on its entire domain, that is, from 0 to infinity. And then finally, because we don't have to lift our pencil at all when we're drawing this graph, the graph is continuous on its entire domain, that is, from 0 to infinity. Once more, let's consider what this looks like on a calculator screen. We're going to go to y equals, and we're going to put into the calculator the square root of x. And as we press graph, we see the shape that we came up with when we did this by hand. Continuing on, the next graph that we want to consider is the cube root function. Here, we're going to do something similar, noting that we can take numbers that are negative in this case. In fact, we can work with numbers that are nice to work with, but that would give us integer values as their cube roots. For instance, I'm going to choose negative 8 to substitute in for x. The cube root of negative 8 is negative 2. I can then move to the negative 1 and take the cube root of negative 1, which gives us back negative 1. The cube root of 0 is 0. The cube root of 1 is 1. And the cube root of positive 8 is positive 2. Let's plot those 5 points. We have negative 8, negative 2. Negative 1, negative 1. 0, 0. 1, 1. And 8, 2. Connecting the dots, we have a nice curve. And now let's identify the properties that we've become familiar with. The domain. As we move from left to right, we notice that we'll pick up all values for x. That's negative infinity to infinity. For our range, we can note that this graph is gradually decreasing, but can continue to decrease infinitely. And same thing with it going up. So our range is also from negative infinity to infinity. As we move from left to right on the graph, we're continually increasing. So it increases over its entire domain from negative infinity to infinity. And finally, since we do not have to pick up our pencil as we trace the graph, it is continuous on its entire domain. And that is also from negative infinity to infinity. Once again, let's move to the calculator screen to see how to graph this. To come up with our cube root, I'm going to go to the math menu on this calculator and pick up the cube root function, and then we'll have the cube root of x, which now gives us the graph that we saw earlier. The next graph that we want to consider is not raising to a power nor taking a root. Instead, it's our absolute value function. Let's look at that now. We have f of x equals the absolute value of x. In our same manner, we want to substitute in values for x. We can substitute in negative values. Let's substitute -2, -1, 0, 1, and 2. The absolute value of -2 is 2. The absolute value of -1 is 1. Absolute value of 0 is 0. Absolute value of 1 is 1. And absolute value of 2 is 2. Let's plot those 5 points. -2, 2. -1, 1. 0, 0. 1, 1. 2, 2. We're going to connect those dots, forming a characteristic V shape. Now, the idea behind graphing all of these basic functions is for us to remember what these graphs look like, their general shapes. So when you see the absolute value function in this format, you want to remember the V shape. Let's go ahead and identify the domain range where it increases and decreases and any kind of continuity that we're going to have. For our domain, we notice that we can substitute into this equation any value for x. We can also see that on the graph. It continues to the left and to the right. Our domain is -infinity to infinity. For our range, we're going to note that as we move from the bottom of the graph to the top of the graph, the first y value we'll encounter will be at 0. And then we can end up with any y value above 0. We could also think about that in looking at the equation. When you take the absolute value of a number, we know that we end up with a non-negative value. Our range then is from 0 to infinity. As we move from left to right on the graph, we notice that this first section decreases until we get to the origin, so until we get to an x value of 0. And then past that point, it increases. So we can write down that the graph is decreasing from -infinity until we come up to 0. And then it increases from left to right from 0 to infinity. And then, since we can draw the entire graph without lifting our pencil, we can note that this graph is continuous over its entire domain from -infinity to infinity. Once more, let's look at the calculator version. We're going to go to our math menu and then over to number in order to pick up the absolute value. We're going to take the absolute value of x and look at a sketch of that graph. And we see our characteristic V shape for absolute value. Now, the absolute value function is actually defined in 2 parts. Let's consider this. If we go back to the graph, we'll note that we could think of this first portion of the graph as being the straight line where we have a slope of -1 and the y-intercept of 0. And so for values that are smaller than 0, we actually get the negative x graph. For values that are larger than 0, we note that we end up getting this straight line that has a slope of 1 and a y-intercept of 0, and that equation would be y equals x. We can write this down in a format that looks like this. The absolute value of x can be said to be equal to 2 different parts. It's equal to x if our x value is greater than or equal to 0. It's equal to -x if our x value is less than 0. This type of graph is called a piecewise defined function. And we're going to look at now a couple of examples of graphs which are also piecewise defined. Let's begin by looking at the function which is defined in 3 pieces. Notice that we have f of x defined as 2 plus x if x is less than -4. It's defined as -x if x is between -4 and 2 inclusive. And it's defined as 3x if x is greater than 2. We're asked now to find 4 functional values. Let's begin with f of -5. To decide what this is going to be, we're going to have to recall that if it's a function, we end up with one and only one answer when we substitute in a value for x. That is, you're not going to substitute in -5 to all 3 pieces. You need to determine which piece to use. We use these side conditions to help us. In our first one, -5, we want to use the piece where x is less than -4. That is, we're only going to substitute into our first piece of the graph 2 plus the -5 to give us back our functional value of -3. For x equal to -1, which piece of the graph will we be using? Well, we're going to use the middle section, where -1 is between -4 and 2, and so this is the section we need to use. We're going to evaluate this functional value by taking the negative of our x value. That is, we'll take the negative of -1 and come up with a value of 1. For f of 0, we go back to our side conditions and determine that 0 is also going to fit in this middle piece. Therefore, we'll take the negative of 0, which is 0. And then for our third entry, we have f of 3. Our x value of 3 fits the third side condition, x is greater than 2. We'll evaluate this by taking 3 and multiplying it by 3 to give us a functional value of 9. Now we're next going to look at another piecewise defined function, only in this case we're interested in graphing it. Here's the function we want to consider. F of x equals x minus 1 if x is less than or equal to 3. F of x equals 2 if x is greater than 3. To graph this, we're going to first identify the fact that if we look at the graph of y equals x minus 1, we're looking at a straight line. If we look at the graph of y equals 2, that's also a straight line. So we have two pieces of a graph, both of which are straight lines. We're going to draw a part of those straight lines. For the first piece, let's consider y equals x minus 1. We're going to take values of x, ensuring that as we substitute in these values, we're going to choose values that fit this side condition. I'm going to go ahead and start at the part that will be the border, that is, right at the value of 3. If I substitute in a value of 3, 3 minus 1 is 2. To choose another point, I want to make sure that I'm picking a value of x that fits this first piece. So, for instance, I can substitute in a value of 0. 0 minus 1 is -1. Now we've already identified that this would be a straight line. 2 points determine a line. Let's graph those points. We can graph our 3, 2, and as we graph it, we note that we want to include that point in our graph. So I'm going to graph it with a closed circle. I'm then going to plot the point 0, -1. And as I do so, I'm going to note then that the piece of the graph I'm interested in is not any portion over here to that's greater than 3 for x, but instead only that portion of the graph where x is less than or equal to 3. Now I'm going to move to the second piece of the graph. The second piece of the graph has the equation y equals 2. Again, I'm going to think of an xy chart, remembering that I'm going to start where the other one left off. Now, one thing to consider here is even though we're not allowing x to equal 3, we still want to know what happens at 3 on this piece so that we can use it as our border. So if x is equal to 3, my y value is 2. We choose now a number larger than 3, for instance 4. If x is equal to 4, my y value is still 2. Be careful when you plot this point. When we're going to plot 3, 2, we want to remember that it's not really going to be in the graph. Instead, it's just a portion of the graph. It turns out that it's superimposed on top of the other point. For that reason, I don't have to worry about excluding it with an open circle. It's already here. We can plot the point 4, 2, and then note that this is going to be a constant function. That is, it continues to the right indefinitely using the value of 2. This graph is continuous. Now it's time for you to try a problem on your own. Again, we're going to try a piecewise defined function. Here's the one we want you to consider. Let's look at f of x equals 4 minus x if x is less than 2, 1 plus 2x if x is greater than or equal to 2. Pause the video now and try to graph this function on your own. Then start up again and we'll look at it together. Now let's see how you did. We're going to start with the first piece of the graph, y equals 4 minus x. This is going to be linear, and I'm going to plot 2 points in order to graph it. For my 2 points, I want to choose my border at 2, and then I want to make sure that I choose a point that's going to give us something where our x value is less than 2. For instance, I'll choose 0. Let's substitute. 4 minus 2 is 2. 4 minus 0 is 4. Let's plot these 2 points. As I'm plotting the point 2, 2, I want to note that it's not really part of the domain of the first piece. So I'm going to plot it with an open circle. Then we're going to plot the point 0, 4. And now I'm going to draw in this piece of the graph where we're going to head toward the left through those 2 points. Then we're going to look at the second piece of the graph, y equals 1 plus 2x. Again, we can identify that this is going to be linear. We can start with an x value of 2 and then choose another x value larger than 2, for instance 3. Substituting, 1 plus 2 times 2 is 5. 1 plus 2 times 3 is going to be 7. 1 plus 6 is 7. And so we'll plot these 2 points. We have 2, 5, which is here, and then 3, 7, which will be a little bit higher off the graph. We're now going to connect those 2 dots, drawing in that piece of the graph. Note that this graph is going to be discontinuous, and it's going to be discontinuous at an x value of 2. So we would say it was continuous from negative infinity to 2 and from 2 to infinity. Now, one special type of piecewise defined function is called the greatest integer function. Let's define that next. The greatest integer function, f of x equals, and here's our symbolism for greatest integer, pairs every real number x with the greatest integer less than or equal to x. We're going to start by understanding this definition in a t-chart. That is, let's substitute in some values for x and see what happens with y. If we start with an x value of negative 2 2/10, we want the greatest integer that is less than or equal to this number. That's going to give us back a value of negative 3. If we start at negative 2, the greatest integer less than or equal to negative 2 is negative 2. At negative 1 5/10, the greatest integer less than or equal to negative 1.5 is negative 2. At negative 1, we come up with a negative 1. At negative 2/10, the greatest integer less than or equal to negative 2/10 is negative 1. At 0, we come up with a value of 0. Let's continue that chart over here to the right. When we look at positive values, for instance, let's look at 3/10. The greatest integer less than or equal to 3/10 is 0. When we look at 1, greatest integer less than or equal to is 1. At 1 4/10, greatest integer less than or equal to is 1. And at 2, greatest integer less than or equal to that is 2. Let's see what this is going to look like on a graph. We're going to take the values that we just came up with and notice that as we're moving from values, well, let's look at the positive values first. For a value of 0, we came up with a 0. For any value between 0 and 1, notice that we're still going to come up with 0. Now we're going to put an open circle at 1, and we're going to shade in that interval between 0 and 1. Once we get to 1, we'll jump up to that value. For any value between 1 and 2, we're going to end up getting back a value of 1. We're going to shade in this piece of the graph, and then at 2, we jump up to 2. And then that continues along the way. For positive numbers, it's easy to see that all you're really doing is truncating. But for negative numbers, it was a little bit harder to understand. But that idea of the graph continuing is constant between these integer values and then jumping up as you get to an integer value is going to continue. This type of graph continues on in both directions, and it is called a step function for, I think, obvious reasons. When we graph it, it looks like we have steps. Now we've looked at a number of different basic functions, and we've looked at some properties of graphs along the way. It's now your turn to try some problems on your own.